And I'm happy to introduce Sandrine, my co-PC chair. It was a pleasure to organize this program with her, and Dimitri and Amin, who are sitting somewhere over here, who helped with the fundraising in particular in the conference organization. And that brings me to acknowledging our sponsors, JetBrains and Casa. Both of them are supporting our invited speakers, and Bedrock. And so we'll start off with one invited talk by Azalea immediately. And then tomorrow, I would like to invite you for another invited talk by Cesare Kaliski on improved assistance for interactive proofs. We couldn't have this talk last year because Cesare was sick, but we'll have it this year. So I think it's still timely. So with that, I'm going to pass it on to Sandrine, who's going to introduce our invited speaker. And maybe, Azalea, you can switch laptops and set things up.
Thank you, Brigitte. So it's my welcome to the CPP first session. It's my great pleasure to introduce Azalea Raad. So she defended her PhD thesis in 2016 at Imperial College London on abstraction, refinement, and concurrent reasoning. She's a senior lecturer at Imperial College London, and she's also the co-director of the UK Research Institute on Verified Trustworthy Software Systems. Her research is in the area of programming languages and verification, where she worked on non-volatile memory, persistency semantics, weak memory models, program logic, and bug detection tools and techniques. And today she will talk about under-approximation for scalable bug detection. So please, Azalea.
Thank you. Am I on? Can you test this? Yes, okay. Thank you so much, Sandrine, for that wonderful introduction, and thank you all for being here at 9 a.m. on a Monday. Although I was here at 9 a.m. yesterday on a Sunday, so it's not as bad as that. It's my first time giving a talk in CPP, so thanks again for having me. And as the title suggests, this is about under-approximation for scalable bug detection. So let me just dive in case you haven't heard of under-approximation in this context, tell you what I mean by that. So this is the CPP community, so I'm not surprised that all of you know a lot about verification in general. And as you know, in the verification community, there has been a lot of formalisms, a lot of techniques for reasoning the correctness of programs, verifying programs. And typically by that we mean we want to prove the absence of bugs. So given a program, we want to show that it doesn't have any bugs. Of course, correctness has different meanings in different contexts, depending on the kind of property that you want to prove. But the general idea is that you want to show that there are no bugs. And these techniques are instances of what we call over-approximate reasoning, because what they do is that they over-approximate or overestimate the set of possible program behaviors, because if you can manage to show this over-approximated, overestimated set of behaviors doesn't have any bugs, then by definition, the actual set of program behaviors is not going to have any bugs either. And unless you've been under a rock for the past 2 decades and you haven't heard of separation logic, you would know that there have been huge advances in compositionality thanks to things such as separation logic, which buys us compositionality in both code, meaning that we can analyze code fragments in isolation rather than having to analyze huge programs at once, but also in terms of resources, like the amount of state or heap or memory, whatever you want to call it, accessed by a program. So we can focus on bits of the state, bits of the machine that is accessed by the program rather than the whole machine. And the huge advantage of all of these techniques, the compositional ones, is scalability. They allow us to scale our techniques to not only huge code bases, but also to large teams, and which is particularly important for CI/CD, continuous integration, continuous deployment, and so on. So what all these techniques have in common, at least up to a certain degree of abstraction, is that, like I said, we can think of them all as instances of over-approximate reasoning. And the idea behind all of them, more or less, can be captured by the good old Hoare triples. Again, this is CPP. I assume that at some point in your lives, you've all seen a Hoare triple and you know what it means. But just a reminder that when I write a Hoare triple like that, PCQ, it means that given an initial state S in P, if I run program C on S and it terminates, then I will end up in some state S prime that is in the set Q. So in a sense, Q is an over-approximation, is a superset of all the set of program behaviors of C starting from P. So that's the subset inclusion up there. The lighting, at least from this angle, isn't great, so I hope you can actually see it. So this is what we mean by Q. It's an over-approximation because Q is over-approximating the post state. So pictorially, I could represent this as that. So if this inner black oval, if you can see colors, is the actual set of post states, you can think of Q as this outer encompassing over-approximation that includes the set of post states. Now, as you know, verification is hard, not only because, well, code bases are large and there's all the human factor and the large teams, but also because programs are often wrong. And there are practical concerns, like when you have to reason about large programs with loops, you have to come up with techniques to generate loop invariants. There's been a lot of successful research in that area, but it is a difficult problem. And often what happens is that we realize that, okay, all of these techniques that we have an arsenal of weapons these days, lots of amazing tools out there, but a lot of times they still fail to verify the program, sometimes for the simple reason that the program is wrong, so they can't be proved correct. So in those cases, we still want to deliver something useful to the developers. So what we do is we do the next best thing. So we say, okay, we can't verify the program, we can't show that it's correct, but what we can do is actually use these tools to find bugs, to report them to the developers so that they can fix their code and repeat the cycle, then try to verify the program again. And this is where we get into a little bit of a pickle because, okay, let's say you find a bug and it happens to be in this set of post state in the black bit. So that's a true positive. It's an actual bug. It's reachable by the program. That's great, thumbs up. And so these are true positives. But what could also happen is because Q is an over-approximation, you could find something and report it as a bug that is actually not reachable by the program. Because we've overestimated the set of possible program behaviors, you could find something that you think is reachable by the program, but it is not. Then if you took this back to the developer and said, here's a bug, they might rightfully return to you saying, please get away from me. This is not a real bug. This never happens, right? And over time, if you keep doing this, the developers will end up losing faith in your tools. Right? So you want to avoid that. And this was exactly the story of Peter O'Han and his experience when he went from academia to industry with the Infer tool, because after a while he realized that the first mantra of program analysis should be not to spam the developers. And the problem that we had, partly, was because of clash of principles, because we had developed techniques that were meant to be used for verification to prove the absence of bugs. And then somehow we ended up using them for showing the presence of bugs. We were using them for bug catching, which is what led Peter O'Han to, right, I broke my own introduction, to incorrectness logic. So he was like, okay, so we really want a formalism mechanism for detecting bugs, and we have all these formalism, but they are for verification. So what if we just went back to the drawing board and came up with a logic for a formalism that allowed us to do bug catching? And this is when he introduced incorrectness logic, and as of this week, incorrectness logic is 4 years old. It was introduced in POPL 2020, and it has led to a barrage of research in the area. In fact, tomorrow there's an incorrectness workshop, and you're all welcome to attend. And Peter will be delivering the keynote, of course. Right, so this was all a very long prelude for me to motivate what incorrectness logic is. So actually, let me tell you what incorrectness logic is now, formally. So we had these triples, Hoare triples that you saw, which are over-approximate triples. They over-approximate the set of possible program behaviors. So now, let's take that definition, which talks about over-approximation, and flip it on its head. Let's change the direction of subset inclusion. And since I changed it, let's also change the color, so it's now blue. And I'm going to write a different kind of triple. So this time, you will see that Q is a subset of set of possible program behaviors. So it's an under-approximated set of possible program behaviors. And this is what we mean by under-approximation. So how do I read this triple? Formally, or semi-formally in English, it means that every post state S in Q can be reached by running C on some pre-state S prime in P. So if I go back to my pictures, if this was the over-approximation picture that I had, now I have this situation where the set of post states is smaller than the set of post states I consider as part of my specifications are smaller than what's really happening. So by construction, any bug that I find with this formalism is going to be true positive. So I'm never going to have false positives by construction. Of course, this comes at the cost of missing some potential bugs, because there could be bugs that are reachable by your program, but you're not considering them as part of your under-approximation. But remember, our number one priority is to eliminate false positives, and that's the price we're willing to pay for them. So it's not perfect, it's not complete, you will miss bugs. If your tool doesn't report bugs, it doesn't mean that your program is verified, but whatever you report will be a true positive, hopefully. There are some caveats there, and hopefully I'll get to them in a minute. Okay, so I'm going to show you a little bit more about under-approximation or incorrectness logic in general, but I need a tiny bit more notation. So the incorrectness triples that we write are typically of this form. They have one extra component, this epsilon here, that's the exit condition, and it talks about how your program terminated. Did it terminate normally, under normal circumstances, without encountering any errors, or did it terminate under erroneous execution? Which is error. For instance, if I run an assignment, I can show that I can reach a state in which x and y are equal and they hold value v if initially y was v. And that's a normal execution. On the other hand, if I execute an explicit error statement, such as assert false, then of course my program will terminate erroneously. The state will not be changed. Whatever it was in the pre, it will still be in the post. Okay. So I'm going to also write down another formal definition, equivalent formal definition of the triples, because it will come in handy later on. So this was in terms of the subset inclusion. Here I'm literally writing down the definition that I said in English, that every post state in Q can be reached from some pre-state S prime in P, and this means that S prime and S are in the semantics of C. So that's the reachability part. Right, so why is under-approximation powerful? So intuitively, we know why it is, because, well, A, it eliminates false positives. You only focus on untrue bugs. But also, it leads to even better scalability than all the techniques that we've had so far. And I want to show you why. So let me show you the first principle I've written about programs in an under-approximate fashion. So sequential composition rule, you would all know it from Hoare Logic. But here we have one extra rule to deal with errors. So this one says, if you run a program C1 from P and it ends up in an error state, it terminates erroneously in states Q, then the whole thing terminates erroneously. So you have this short circuit in semantics. So if the first part of the program encounters an error, then the whole program encounters an error. And this is just because we have introduced this error, this short circuit in this, like you can think of it as exceptions, for instance, the errors that actually halt the program execution abruptly at once. There's, of course, I don't know why this is skipping twice sometimes. And there's a rule that should be very familiar to you from Hoare Logic. This is more or less the sequential composition rule in Hoare Logic that says if you run the first part of the program, C1, and it terminates normally in states R, and from then on you carry on executing C2, then you can glue them together. Right. Now, this is one of my favorite rules about under-approximate logic, under-approximation, incorrectness logic, and it's talking about conditional, well, branching. So here I write C1 plus C2. You would know this notation probably to mean that non-deterministic choice, either execute C1 or C2. So it's branching. Like think of it if then else statements with like a random condition. Right? Now it says, if you want to show that this branching program, under this branching program, you can reach the state in Q from P, it's sufficient to show that some branch does this. So if you can show that Q is reachable from some branch of execution, either C1 or C2, then you can reach it under both branches. And this is in stark contrast to the condition or branching rule that we have in Hoare Logic, where you have to show the same thing for all branches. So you have to show that PCIQ for all branches to show that that's the behavior that you have. And the reason this is useful is because it allows you to forget branches and drop parts. So halfway through your analysis, it's actually sound in under-approximation to ignore certain execution parts. And of course, as we know, one of the problems in over-approximate program analysis is this state space explosion due to branching. And here we can tackle it by bounding the number of branches that you execute or you consider at any one time, and we can do this in a sound fashion. It will still be a sound under-approximate reasoning technique. And similarly, for loops, this rule says, well, okay, I write C star, this is the clean star, that says execute C 0 or more times. So either I execute C 0 times, in which the states are not changed. I go from P to P, or I unroll it once. So if I want to show Q is reachable from executing C in a loop, then I can show it that it's reachable by unrolling it once. Right? And again, you can, why are you skipping twice? This allows us to essentially implement bounded unrolling of loops in a sound fashion. So rather than having to worry about things like loop invariance and showing that no matter how many times you iterate a loop, you have this specification and you can meet it, then we here soundly consider a bounded unrolling of the loops and say, okay, up to this number of unrollings, this behavior is reachable. Okay, so this was incorrectness logic in a nutshell. It's under-approximate. You can think of it as an under-approximate analog of Hoare logic, and it's a formal foundation for bug catching, at least the way Peter initially envisaged it. But of course, it suffers the same limitations that original Hoare logic did, in the sense that it is used for global reasoning. It doesn't have the compositionality that later on we actually got from things like separation logic. And as a result, it can't reason about things such as memory safety properties in programs where you have aliasing and pointers very well. So the natural next question that we all posed to Peter was, why didn't you consider an extension with separation logic? And this is when Peter asked me to join him, and we started working on incorrectness separation logic together. Now, I assume in this room everyone knows what separation logic is. Hands up if you don't know what separation logic is. Good, so I will skip the next couple of slides. You all know, I'm preaching to the choir, so you all know what separation logic is and why it's good. So separation logic, frame rule, remember this is our number one priority. We want to buy the compositionality that separation logic has, but in an under-approximate fashion. And of course, we want to preserve these local axioms that you would have with minimal footprint, right? So just to introduce my notation, here I am considering a very simple language with heap updates, or write, lookup, or read, allocation, and deallocation. And these axioms should be familiar to all of you if you know separation logic. So now we want to take this incorrectness logic that you saw, and we want to put it together with the main hero of separation logic that does most of the heavy lifting, the frame rule, right? And just a refresher, the frame rule says, okay, if you manage to prove a specification PCQ, as in you go from states P to Q, then you can extend your states and actually derive a similar specification when you start in a larger state by tacking on additional resources R on both sides, provided that, of course, those resources are disjoint or compatible, whatever notion of fiction of separation, all these works that have been around for a long time, where your star means. So you want to put these two together and get incorrectness separation logic. So like any good researcher, what we did was the path of least resistance. So what's the simplest thing that we can do? Let's take the existing axioms and exactly as they are, recast them in the under-approximate world. So this is my heap update axiom, exactly as it was before. No surprises, I've just written it. I've added an OK saying that I can update the heap normally. But since we're also considering errors here, I can also write something like that says, if X is null to begin with and you try to write to it, then of course you get a null pointer dereference. That's an error. Similarly for heap lookup, if I'm trying to read from something and it's null, I get a null pointer dereference. The OK case is identical. Heap allocation and the allocation as before, plus the null case. And this is where things break down. We try to prove the soundness of this logic and we immediately fail. And the culprit is this free axiom, the deallocation. So let's see why. So this is my free axiom, as it is in standard separation logic. Now what I can do is, remember I want to preserve the frame rule as is. I want to have that reasoning principle. Now I can add on x points to v on both sides. So since you're all separation logic whiz, what do I get on the right-hand side? M star anything is that thing itself. But I can't, of course, duplicate x points to v with x points to v, so I get false on the left-hand side. Now, if this was an over-approximate triple, it would be no problem at all. If it was a Hoare triple, it would just be vacuously true, right? Not if you agree. Good. But in the under-approximate setting of ISL, this is incorrect. Because if you remember, this is the meaning of the triple. It says every state in which x points to v can be reached by executing free on some state that satisfies false. So these things on the left-hand side are existentially quantified. And false is an empty set of states, so nothing satisfies false. So I've derived something that's obviously not valid. And the reason is that this original axiom of the allocation in separation logic is lossy. After you free a location, you forget that that location was ever allocated. So in a sense, the model was a bit non-monotonic. So the amount of heap resources that you had could grow through allocation or shrink through deallocation. So what did we do? The next simple thing. So we started tracking the allocated locations. So instead of writing this axiom for the allocation, when you free x, we said, OK, we're going to remember that x was previously allocated. So we're going to write x is deallocated with this points to and a line through it. And this is also a linear resource. It can't be duplicated. And it has the same composition rules as a standard points to. So x is deallocated. Yes, these are the standard points to axioms that we usually have. But here we also have, OK, it can't be star conjoined with itself. You can't have two copies of it because it's a linear resource. But also, of course, you can't have x is allocated and holds v star x is deallocated. Obviously, they're contradictory. So now if I play the same dirty trick as I did before, and I start starring things on the right-hand side, what I end up is false on both sides. Right? So, and that triple is vacuously true, so the logic is still sound. And so what we did was we just took this lossy model of separation logic, the original model. We started tracking these deallocated locations. We made the logic monotone in the terminology that one of the people at Imperial a while back introduced. And this actually recovered a property that the original separation logic lacked, which is the footprint property. And there is this result that says if your model has this footprint property, you need this footprint property for completeness. And because the original model of separation logic didn't have this footprint property, that's one of the reasons it was incomplete. Anyway, so if I go back to the axioms, I've changed the free axiom so that when I deallocate, I now remember that x is deallocated. The null case is exactly the same as before. But I also have one more case now that says, well, if x is deallocated and you already deallocated and you try to free it again, then of course you'll get an error. And this is, of course, a double free error. Right. So again, the write, the read, and allocation as before, except that I also have now the allocated cases. So if you try to write or read from a location that's already deallocated, you'll get a use after free error. So those are new errors. OK, so to sum up, this was the first part of the talk, incorrectness separation logic, a combination of incorrectness logic with separation logic, which had to change the model, and we got a monotone model that recovers the footprint property, which is necessary for completeness. And then we thought, OK, what should we do next? Well, I started the talk by saying, oh, under-approximation is great. It leads to even better scalability. So we really needed to put our money where our mouth was, right? So we had to test the metal of this new logic. So the next thing that we did was like, OK, what if we actually implemented the program analysis based on this idea? This is the next part of the talk. Our tool, a prototype tool called PulseX, which is now fully deployed at Meta into the Infer Pulse framework based on under-approximation incorrectness logic. OK, so in a nutshell, what is PulseX? It's an automated program analysis, so it's push button. It requires no effort on the side of the programmer. They literally press go, and it goes. And it's specifically targeting memory safety errors. And by that, I mean null pointer exceptions, use after pre, as well as memory leaks. I didn't show the theory here, like the axioms for memory leaks, but we handle that too. Of course, it's underpinned by incorrectness separation logic. So by construction, it doesn't have any false positives. Notice the asterisk. I'll come back to the terms and conditions in a minute. This is Britain. We love our terms and conditions here, right? There's always a caveat, but I will come back to that later. It's interprocedural and bi-abductive. These are buzzwords I'm throwing at you. Hopefully, by the end of this section of the talk, it will become clear what they mean. And it's compositional, meaning that you can reason about code fragments in isolation rather than everything at once, and it is deployed at Meta. So how did the tool do, just before I introduce the technical details? Well, in terms of performance, it was comparable to Infer. And remember, Infer has been developed over a decade, more than a decade, by a very moderately sized team of really talented engineers. Whereas this was an academic tool. There was one engineer at Meta helping us and one academic working on this. And yet, we had performance comparable to Infer without any of the optimizations that they did. I'm sure it's getting better and better every day now. And in terms of fix rate, meaning the percentage of bugs that were actually fixed after being reported, we were either comparable or better than Infer. And by Infer, I don't mean the framework Infer, I mean the original one based on over-approximation. So, how does it work? So in a nutshell, like I said, these buzzwords will become clear. It's compositional, begin anywhere. What do I mean? I mean that if you have a large piece of code and you want to analyze it, the way you do it is chop it up to smaller bits, analyze each bit in isolation, and then put them together, find a method of putting them together to get the result of the overall program. So how do we chop up programs? Well, we do it at the level of procedures, so that's the granularity of our chopping up. So if this is my call graph, F1 calls F2, these are all procedures, I will analyze each one of them in isolation and then put the results together. And the way we put things together is under-approximate by abduction. So if you don't know what by abduction is, it doesn't matter. It's a technique that has existed for a long time. It's used in the original Infer, correctness-based Infer. And what we did, we used it in an under-approximate fashion. And I will become clear what I mean by that. And what we get in the end is incorrectness triples, these ISL triples that you saw. So we will be looking for the erroneous ones that talk about bugs. Right, so to do this, we analyze this procedure F, each procedure F in isolation, come up with its summary. So to do this, we have a summary table F. Initially, we only assume that we have these local axioms of primitive operations like heap update, heap lookup, and so on. And then we use by abduction, which you don't need to know the details of, to come up with the summaries of these procedures. And every time we do, we extend this summary table, the new summary. And the by abductive mechanism, we did not implement anything new. We tapped into the existing by abductive mechanism of Infer, except that we did it in an under-approximate fashion. So instead of having to worry about, for instance, loops, we just unrolled them in a bounded fashion. We had a cap saying, OK, consider up to 20 unrollings or 50 unrollings and things like that. And same for branches. We had a cap saying, OK, when you have programs with many, many parts, we had a cap saying, just consider up to these many branches. Because again, remember, we can soundly ignore branches in under-approximation. So let's look at an example. Ignore the ridiculous names that I can't even pronounce, SSL, XZ, prepend. The caveat, the disclaimer here is that I will show you a few examples. They're all heavily stylized. I'm only showing a few lines of code, only the relevant bits, but they're more complicated than they are, I promise. And all the examples I'm going to show you today are from OpenSSL. They've been reported, and they have been fixed since then. So this is a very simple example. It calls appmalloc, which itself behind the scenes calls something called cryptomalloc, which is a malloc wrapper. So it tries to allocate some memory. And once it's done that, it tries to initialize it with 0, call in memset. So very simple. It turns out cryptomalloc may return null, so the allocation is not guaranteed to succeed, right? And of course, if it returns null, then when you try to memset it, you will get a null pointer reference. So that's a potential error. So it's very simple to come up with a summary of that. You can see that one potential summary for app malloc is this, that it can terminate normally and return null in an EXC. And as a result, when you have memset starting from EXC being null, you get a null pointer dereference. So we can see that now we can combine these two summaries because the post here matches the pre here and get this summary. That I don't need any resources, and I could get a null pointer dereference error. So we reported this error back to OpenSSL developers, and they immediately came back and said, no, sorry, this is a false positive, because this app malloc actually will not return if the result is null. And we were baffled at this point because we had a trace showing, hey, here's this trace, things are going wrong, there's a null pointer dereference. And it turns out there are two versions of app malloc in two separate files, and they were calling the wrong one. And we said, very coyly, we think you're still wrong because you're calling this other one, and this other one doesn't behave as you said. And at that point, the developer acknowledged that, yes, we should, A, call the right one, we should fix the implementation of the other. So this was eventually fixed. Now, Okay, so I did say I will come back to the terms and conditions. So let's look at those terms and conditions. Let's say that I find a bug, as in I find one of these error summaries. Do I always report it? Because I said there are no false positives, right? What do you think? I won't suspend you for much longer. The answer is not quite. It depends. What does it depend on? Well, okay, let's look at a simple example. I have foo, takes one argument x, immediately dereferences it and writes 42. So very straightforwardly, I can come up with this summary from this right axiom for foo that says, well, you have a null-pointer dereference when x is null. Now, let's say I do report this to the developer, this null-pointer dereference. Well, then the developer could come back and say, well, yeah, cool your horses. I know there is a potential null-pointer dereference here, but I'm careful. I never call foo with null. I always pass it the right argument. And if I decide not to report it, then when should I report it? So to distinguish these two scenarios, we came up with this criteria of when is an error a manifest error, as in we should definitely with confidence report it. So what we call a manifest error is an error that occurs regardless of what inputs you pass it. Remember there the problem was that if you give it x as null, then you get an error. So a manifest error is one where the error occurs regardless of what input parameters that you have. So there is a formal definition that I'm not going to go into, and an algorithmic justification that actually implies the formal definition. So for instance, here, you would see that I've even abstracted away the arguments of the procedure. It doesn't matter what you pass it. This error always occurs regardless of the input. So here we can be confident that this is a manifest error, because it's always possible. When I say it always happens, I don't mean for all executions. I'm saying it's always possible for it to happen, regardless of the input. There's always a trace, regardless of input. So the dual of a manifest error is what we call a latent. So if it's not manifest, it's latent. And here's another example from OpenSSL. This chop-up args takes an array of arguments, args. And this args component args has two components. The count, which is an integer, and data, which is an array. Now, if the args that you pass has count 0, then what the implementation does is first sets it to 20, and then populates data by allocating some new memory. And it does that using this procedure that you saw on the previous slide. And afterwards, then it goes through this data array and sets everything to null. OK, so as you remember, there was a null pointer dereference here. So if you go to that branch and you get this null data array, then later when you try to write to it, you will get a null pointer dereference again. Now, what is this error? Is this manifest or latent? I kind of flashed the answer, but anyone with the justification, do you think this is latent, manifest, and if so, why? OK. It is 9 a.m. after all, so move on. So this is a latent error, because this error occurs only for inputs where they have a count 0. So if the count is 0, then you will take this path and get a null pointer dereference potentially. So this is something that we will call latent. We will record the summary and hold on to it like a vengeful friend. And then later on, if we come across a call site that calls chop-up args, and we can show that it is calling it with an argument that has count 0, then at that point, that error becomes manifest, and then we report it. OK, so this is latent because it only happens on certain inputs. I also said that we reason about memory leaks. So I want to show you a little bit of that, an example. So again, this is from OpenSSL. It's in something called S-server, which creates an SSL TLS server. Important bit of code. So what it does, it creates a new buffer. That's all you need to know. A buffer of entries. It creates a new entry, does some stuff, adds that entry to the buffer, does some more stuff, and when it's done, it basically deallocates everything in the buffer by calling this free all. So it iterates over everything and deallocates them to make sure it reclaims the memory. Now the problem is, if you call push with IO being null, it silently does nothing. So if you pass it a buffer that is null with an entry, it just does nothing, which means that your entry is now not pointed into. So it's kind of dangling there. As a result, if IO was null, it's now not in the buffer, and later on when you call free all, you won't be reclaiming that bit of memory. So you will be leaking it. So we run PulseX on this, and the reason I like this example is because, okay, it was 400 plus lines of code. That in itself is not impressive. There were several loops in the program. They were nested, and we did it with bounded unrolling. In fact, the cap, I think, was at 10 or so. PulseX immediately found this error, this memory leak. Infer struggled and eventually timed out. It couldn't. And it's because there were several loops in the middle, and Infer was struggling to come up with the right invariance and doing the right thing, and it could never get past those loops to get to the error. And this is where the difference between under versus over approximation really comes across. Okay, so some more caveats. Remember, terms and conditions. The way we Brits like to do it is do it in installments, so you don't know what's hit you, right? So there are times that we can't guarantee the absence of false positives. The first one being when we have unknown code. So let's say you have calls to procedures that are proprietary code. We don't have access to the source code, so we can't analyze them to come up with a summary. We just treat them as skip. Bless you. The second scenario is when we have, it's to do, source of false positives is to do with our arithmetic solver. And as you know, this is, like in general, this is orthogonal to over versus under approximation. When it comes to arithmetic solvers, any solvers in general, we have two competing desiderata. We want them to be fast, and we want them to be accurate. And they're usually one or the other or somewhere in between. Right? They're either fast and simplistic or slow but accurate. So what we decided to do was take Tony Hoare's advice that says, essentially, idealism is for scientists. Engineers need to be practical and make sacrifices. So this is what we did here. We went for a fast but inaccurate arithmetic solver, which meant occasionally we got false positives because our arithmetic solver was giving the wrong result. And that's terms and conditions done, caveats done for now. So in the remaining 5 minutes or so, I want to talk about some other extensions of incorrectness logic and under-approximation that we've had. So I'm only going to mention them. I'm not going to go over the details. So we have 3 pieces of work since then. The first one being the next natural extension. How do we use incorrectness for finding concurrency bugs? So here is the original CSL, concurrent separation logic rule, this reasoning principle that says if you want to reason about a concurrent program, you want to be able to analyze each one of the threads in isolation and combine the result. And we wanted to put these two together and get CSL, concurrent incorrectness separation logic. So we did that. I'm going to skip. And we have a general framework that can be instantiated for finding different classes of concurrency bugs. We've shown how to do it for detecting data races. We've done this to show how to detect deadlocks and also memory safety bugs. The next thing, and this was all when I was doing some consultancy work at Meta. Then a guy from Bloomberg approached me, who is actually here, will be here tomorrow as well, and said, well, this is all neat, but what if we just use them to find security exploits? It's the hot thing, right? And so we started working on an extension of CSL that allows us to actually deal with security exploits and vulnerabilities, and this is what we did. So we have this other logic called CASTLE, concurrent adversarial separation logic, that allows you to find things like information disclosure attacks, buffer overflow attacks, and so on. I didn't get a 5-minute warning, by the way. I don't know when it's coming. Okay, because it's 40 past. Anyway, and of course, as before, because these are all under-approximate analyses and techniques, by definition, by construction, you have this no false positives guarantee. And we're currently working on doing things like actually building tools that would detect exploits, and then going further. What if we synthesized and generated the exploits ourselves? Money, money, money. Right, I don't mean that. And the third extension, which I'm going to talk about a little bit more, is using under-approximation for detecting non-termination bugs when your program doesn't terminate, it diverges. And that's been the most fun I've had in many years doing research. It's been really fun doing this, working with Peter and several other amazing people who are in the room. And so this was nice because there has been a lot of really great work on showing program termination. People such as Byram Cook, Rupak Majumdar have done great work in coming up with analysis for showing that the program does terminate. And that's inherently a over-approximation problem, because you have to show that every trace of the program and more terminates, right? So if I have a program like this with multiple branches and I want to show it terminates, I have to show that every branch of the program terminates. On the other hand, showing non-termination is an inherently under-approximate problem. If you want to show that your program doesn't terminate, it's sufficient to show that some branches don't terminate, not all branches, right? So if I have this program, again, 2 branches, the left-hand side is skip, and this is while true is skip, it's sufficient to show, well, of course, this branch doesn't terminate. And this power of dropping branches and doing under-approximation comes really handy here. So this is what we've done. We've called it under-approximate non-termination logic. Unter, if you speak German, it also means under, so I was very pleased with that. And it supports things like unstructured constructs, such as go-tos, and breaks and exceptions and things like that, and detecting different sources of non-termination because of infinite loops, infinite recursion, or these cyclic go-to loops that you could potentially get in your code. So what are the reasoning principles of Unter? Well, it's essentially, you want to show that sometimes, like some parts of the program terminates and results in something, and from then on you get divergence. So essentially the proof principles are what you had in ISL that I showed you at the beginning, plus some new rules for divergence. And those rules are mind-blowingly simple. We couldn't believe how simple they are. So we're going to write triples like this, PC infinity, to mean that C has some divergent trace starting from P. So pictorially, again, this is my initial state P. What I want to show is that there is some state that if I started from here on, I can keep on forever ad infinitum and never terminate. So how should we do this? Well, what I can do is, first, if I manage to show that C1 doesn't terminate, starting from P, then of course C1 followed by C2 doesn't terminate either. The first part of the program is not terminating, so of course the program doesn't terminate. Similarly, again, if the first part of the program terminates, going from P to Q, and this is what I mean by ISL triple, so this is basically the kind of triple that we saw. So if the first part of the program terminates, transforming P to Q, and then starting from Q, the second part doesn't terminate, then the whole thing doesn't terminate either. So, and what about choice? Well, if you have multiple branches, remember, it's inherently under-approximate, and some branch doesn't terminate, then the whole thing potentially doesn't terminate either. So for either of the i's here, 1 or 2, if C1 or C2 doesn't terminate, then the program doesn't terminate. And again, here we use the trick of dropping parts and just focusing on only certain executions. And what about loops? The hardest part. Okay, this is the hardest thing I will show as part of this analysis. Well, it says that here, if you want to show that the loop doesn't terminate, right? Thank you. I have less than 5 minutes, so it should be okay. If you want to show that this loop doesn't terminate starting from P, well, it's sufficient to show that one iteration of the loop doesn't terminate. Let's say you have a nested loop. So if you show that an inner loop doesn't terminate, then of course the outer loop doesn't terminate either. And there's another rule which is more interesting, but I said extra condition omitted. That condition is very straightforward, but just for simplicity, I've omitted it. This one says that, okay, let's focus on one iteration of the loop, and let you start from P. And if you go back to the same state, so if you're from P, you go to another state in P, again to another state in P, ad infinitum, so your program doesn't terminate. And this is enough to show non-termination for loops. So we have this theory, and it has been extended, like I said, by some people in this room. Caroline, who's sitting over there. So this was the work that I had on very simple stuff, just handling loops. Caroline has extended it with go-tos, with exceptions, with recursion, which was not straightforward, but she's done that. So we're very pleased with the theory. And then again, we thought, what if, okay, this is all interesting for us. You know, after all, we're in it because it's interesting rather than it's impactful. But the industry, all they care about is impact. So what if we actually implemented this? So we went back to Infer and Pulse, in fact, and said, let's extend Pulse for this divergence analysis. And we now have a working prototype that detects non-termination bugs. And specifically, we have been focusing on denial of service attacks because impact, right? So this is another well-known security bug or security exploit where, for instance, you can bring down a server through essentially something as simple as a non-terminating while loop. And we've been finding a number of them. Of course, this is a prototype. It's not yet ready for full deployment at Meta or anywhere like that. But the plan is to eventually polish all the rough edges and incorporate this as part of the full Pulse platform at Meta. And the results so far are very promising. So this brings me to the end of the talk. I've talked about under-approximation, the philosophy, and why it matters for bug detection. And so far, it has been very promising for us. We have pursued several directions for detecting memory safety bugs, use after freeze, null pointer exceptions. This was in PulseX. Memory leaks, also included in PulseX. We've talked about detecting data races and deadlocks. Now, these tools came before under-approximate theory. There are two tools available at Meta called RaceD and another thing for deadlock detection, which is for some reason unnamed, but they're both based on under-approximation. After the fact, we showed that those tools can be exactly justified by instantiations of this concurrent framework that we had for detecting data races and deadlocks. So those are also instances of under-approximation. Security exploits is one thing that I just mentioned, I haven't talked about, and of course there's divergence, and our prototype, Pulse Infinity, for detecting divergence bugs. And I want to finish with this quote from Patrice Godefroy. If you were lucky enough to be in the O'Han Fest yesterday, the fest we arranged for Peter O'Han, he was there and he gave an amazing talk. And this guy was ahead of his time by about 15 years. So back in 2005, when we didn't even know what under-approximation meant in that context, at least in our field in terms of program logic, he was like, okay, he actually said, I was a little annoyed with my colleagues. Everyone was focused on verification and showing no bugs. And I was in industry seeing that no one actually cares about verification unless it was helping them better their code or find bugs. So he wrote this statement that's one page and still on the web that says, guys, most program analysis and verification seems confused about the ultimate goal of software defect detection. The main practical usefulness is the ability to find bugs. So we want to help developers find bugs and detect them, not to report that no bugs have been found. And he did this in 2005, and it took the community, someone as smart as Peter, let's say another 15 years to actually potentially come up with a formal foundation to justify bug detection. So back then he was talking about sound bug detection, i.e. finding bugs that were true positives, so justification that this is a true bug. And thankfully, thanks to the work of people such as Peter, we now have that formal foundation. Thank you so much.
Do you have questions? You should stand up and come to the mic here to ask your question, please.
State your name and rank.
Hi, I'm Jan Menz, PhD student at MPISWS, and I want to thank you for the very interesting talk, and I have a question. I'm a bit unsure how this looks like in practice. If I have a program I want to find bugs in, and I boot up something like incorrect iris or something, what do I put in the post condition? Presumably the original, the normal specification won't do much good because it only shows that it doesn't always go wrong. So do I need to know which bug I want to find to know what to put in the post condition, or is there something general?
So if we're talking in the let's say, I assume you're talking about in the context of a practical tool like Paul. So those tools are push button. You don't need to give them anything. You just give them your code, and they will find the bugs. But of course, only a certain class of bugs. So for instance, PulseX only detects memory safety bugs, null pointer exceptions, use after free, memory leaks, and things like that. If you pass your code and it's concurrent to RaceD, then it will detect, you again, use things like by abduction and whatnot to detect data races. Similarly, this other tool will only find data deadlocks. But they're all zero effort. You just give them the code, run the analysis on them, and that's it. Now, if you're talking about, I have some correctness specification in Iris, does it work as an incorrectness specification? Of course not. They have an entirely different semantic.
And these tools, essentially, what they put in the post condition would be something like, okay, there's use after free error or something like that?
So you saw those like triples that I wrote. They're literally separation logic assertions, by bit, like the spatial part and the pure part, and these error tags. And those error tags here, I abstracted and just wrote error. They actually specify saying, oh, this is a use after free, or this is a double free. So they classify it as such.
Okay, thanks.
Vadim Zaliva, University of Cambridge. I have a question about your...
I'm so kidding. Guys.
have a question about epsilon, your error definition. So it's a little bit imprecise because, if you're reading about pure functional language, the error could be like, returning none. It might be handled differently. Or if it's C, what would be the definition of error in C language if you're analyzing C programs as you've shown? Can you elaborate on that? So
yes, this was like a little bit what I touched on with the answer. Here we are assuming a heap manipulating language, something like C. In fact, in the context of PulseX, our target language is something called SIL, Smallfoot Intermediate language or something like that. But it's all about a pointer manipulating, heap manipulating language. So we do not dealing with something functional here. And as I said to Jan, these error tags carry a little bit more information. They're not just saying error. They actually say, okay, this is a use after free, or there's a leak, or there is a double free here, things like that. In a functional setting, I haven't thought about it much. What kind of error, well, you'll have to tell me what kind of errors you would want to be looking for and what kind of assertions you would like to write, because I imagine if it's purely functional language, maybe it doesn't make sense to have all these separation logic assertions about the heap.
Have you thought about the relationship between these errors and undefined behaviors in C?
That's a whole can of worms. Well, undefined behaviors arise from number of reasons, right? It could be because you have a data race according to the C standards definition, or it could be because you're accessing something out of bounds and so on. We haven't thought about what it meant in comparison to that because we had a specific target in mind, which is memory safety errors.
Thank you.
Thanks for the great talk. So my question is about separation, a logic for detecting bugs as compared to, let's say, more automated way of detecting bugs, right? Mm-hmm. And in fact, to some extent, I do not so much agree with this slide that you've shown because, well, even though, in fact, most of my work is on detecting bugs, I do think that, that verification is probably the ultimate goal.
Absolutely. We're just not there yet. Okay, so I definitely see where you're coming from. And just to say, I have a formal theoretical background as well, and I agree with that. Verification is the ultimate divine goal that we're all striving for, right? And I'm just saying the technology isn't there yet together. So, and as a result, what we've done is use verification tools for bug catching, and this is what we are objecting to, right? So I think the goal is eventually, the way it is right now, we're running these things in cycle, right? Let's say you run a verification tool on your program, it doesn't succeed. Then what you can do is then go back and run a formally underpinned bug detection tool, and you essentially hoping that in the limit you will reach verification, right? You keep repeating this process until hopefully your code is free of bugs at some point. And I'm saying there is value in doing that, not that we should abandon verification research at all. And also it's about how rapidly your code base is evolving, right? So for instance, a code base such as WhatsApp in Meta that's evolving very, like there are hundreds of commits every day. It's unreasonable to expect to verify that, right? But what we want, and as part of CI/CD, this is what Meta essentially does, it's run these tools all the time, every time there is a commit, to find bugs before they go into production, right? But then let's say you have some other code that is fairly stable and hardly ever touched, like a microkernel code. There is definite value in verifying that, even if it means mechanize it in Coq, right? Because that code is stable, it's not modified or touched very often, and it's obviously critical code, and we should verify that. So it's all about what domain you're looking at, what setting you're looking at, how quickly is that code base changing, and what's feasible.
So yes, so that answers the first part of my question. The second part is sort of related, which is, well, the point of a logic was more towards proving the program's correct. And when somebody designs a logic for detecting bugs and tries to do deductive style bug detection, to me that seems a little too much.
I think that is subjective, and I think what you said is completely valid opinion, so I'm not going to dispute that. In fact, it reminds me of something Peter said when he submitted Incorrectness Logic to POPL. One of the reviewers came back and said, well, this paper legitimizes testing for the first time, because in the verification community, we've all been so snooty about, testing, it's not sound, and this was given a formal underpinning to testing, essentially. But I disagree that it is too much, because, for instance, testing, of course, has been one of the most practical tools that we've had with finding bugs. And again, there's this analogy that people in the literature use, the deletion test. Let's remove all the verification tests that has been done. how much progress do we lose versus let's remove all the testing work that has been done, all the testing that's done in industry. How catastrophic is that? So I'm definitely not poo-pooing testing, but what my point is that testing or even things like bug detection tools that we had, until then, one of the things that they suffered was false positives. And what can help? Formal methods. If you apply formal methods and remove false positives, to me, that's a win.
So something like CLE, for example, do you think that is somehow not sufficient?
I'm not saying that, but CLE has been amazingly successful, but CLE has its own limitations as well. For instance, CLE is not, okay, there is an iteration CLE, but it's no longer stable. It's not compositional. Every time you want to analyze your code, you have to run it on the entire code base. And somewhere like in industry, that's not going to be feasible. Again, I am not trying to pit one approach against the other, but I'm also saying that I do not agree that this is too much because we've had these bug detection mechanisms and we've had false positives. In fact, we've been using tools that were meant for verification and reporting lots of false positives. And this is one step towards allaying that concern.
Thank you so much.
Okay, maybe a last question? One or two last questions.
Thanks for the talk. I'm René Thiemann. I wanted to ask about your counterexamples. Once you find them and you present them to the users, does your tool have any methods to first minimize somehow the counterexample, so somehow minimal counterexample generation from a large one? And you said that you use inaccurate arithmetic solvers during the search process. So do you then perhaps use the more accurate solver before giving the examples to the user to check that once you found an example, it really is a counterexample?
Oh, thank you. Both very interesting questions. Thank you. So the first part where you said, what was it? Do you have a mechanism of essentially just saying like counterexample? Do you have a mechanism for generating counterexamples? We do have these summaries, and often what it says is that it gives a stack trace, but also with annotation saying, oh, this you have a null pointer in the reference here, and it happened because it was called by this method that called that method, and if you pass null here and here. So there's like some English printout, nothing as formal as a counterexample, no. The second thing that you said, remind me again, what was the arithmetic solver. So the arithmetic solver, the answer is, unfortunately here, we were limited by the interests of meta, right? At the end of the day, we were working with them, we were trying to integrate into the framework that they had, and they were not interested in developing a better arithmetic solver, and I definitely didn't have the expertise to do it. So I think there's definitely value in doing that, and what this approach that you suggested is definitely valuable. It's not something we've looked at, unfortunately.
Okay, thank you.
Yeah, go ahead. Yeah, please.
I have a quick technical question. So about the example involving a count of the arguments. So you said that there could be a null pointer dereferences, but that's inside the for loop that is guarded by the condition that I is less than the number of arguments. So that would never be triggered when the count is 0. So as far as I understand,
that part wasn't inside the for loop. It was first checking if the count is 0 and then allocating some memory, and then going inside the loop and setting everything else. I can show you the example again. If I can go back to the right place. Was it this? Yes.
Yes, so
here, there's no for loop. One of the first things it does is check your thing. It says, is it deallocated? Because you set the count to 20, remember? You set the count to 20 and then allocate some memory that could potentially be null.
Oh.
So you enter the loop, but your thing is still null. Right.
Got it, thank you.
Okay. So I think that's the end of the question. Azalea, thank you again.
My pleasure. Thank you.